So good morning. So we're going to continue on with the construction plan tutorials. Volume 1 bridge plan reading. This is episode 5, concrete construction terminology, key terms part 2. So we're going to continue on with even more concrete terms. Here we're going to talk about our chamfer, construction joint, cold joint, and compressive strengths. Number 1, chamfer. It's a beveled outside corner or edge on a beam or column or a triangular wood strip placed in the corner of a form to create a beveled corner. These are used with the states to bevel off any exposed corner that the public can access. This could be a safety issue. A non-beveled edge corner of concrete can injure you if you fall into it or rub against it. I've seen guys get abrasions off of it. So this is a safety issue and it's an aesthetic issue. It makes the concrete look good, clean finish. Next we got a construction joint. It's a separation between two placements of concrete, a means for keying two sections together. As shown here on this abutment, you'll see that the back wall, you see there'd be optional construction joints on the back wall. This is done that the contractor can separate this abutment into separate pours and have these construction joints here in this back wall. Another place that you'll find construction joints is just where two different pours on say a bent here, top of the drill shaft and the top of the column, 3 pours. And what they'll do is when you finish one pour, you'll scar up, take some piece of rebar or something and dig gouges into the top of that, so that when the next pour is poured on top of it and you either apply an epoxy or a moose milk, as some states allow, the concrete will go into those keyed areas, those grooves that you cut, and give a good bond for each different pours. Next thing is a cold joint, construction joint in concrete occurring at a place where the continuous casting has been interrupted. A lot of times this is a no-no. Pours should be continuous, which means that once you start the pour, you don't finish the pour until whatever you're pouring is finished. Sometimes weather, equipment breaking down, trucks not making it. There's a lot of excuses why you get a cold joint, but a cold joint is pretty much where concrete has set, concrete is poured. You've got an open joint there. You got voids, places where water can get into it and ruin the concrete. It's structural issues. So unless the engineer tells you can put a cold joint there, they're pretty much not allowed. And if it is an engineered approved cold joint, then now it's a construction joint. So compressive strength is maximum stress of a material is capable of resisting under. This is a typical concrete mix design submitted by a concrete supplier. Right here we're talking about ALDOT. States, ALDOT classifies their concrete into classes, class A, B, and C. States do the same. All states do the same, but sometimes their 4,000 psi might be a class D or a double A, double B. You just got to pay attention to your specs. But here in ALDOT, it's a class A, B, and C. Class A is your 3,000 psi. It's a substructure and retaining walls. I always kind of keep in mind if earth is touching it, it's going to be a class A. It has something to do with pressure and bearing pressure and all that with its design. Class B is 4,000 psi. You'll see that in superstructure and the roadways. Another thing is, I always say if the public's going to touch it, it's a 4,000 psi, class B. And then you got a class C, which is a 3,000 psi. It's rare. It's for miscellaneous small pours, collars, underground structures, things like that. Could be a class C concrete. The bent, foundation, footing, columns, and caps. The bent, a self-supporting reinforced concrete frame with one or more columns, usually at right angles to the length of the structure it supports. This is a bent. it's at a right angle to your bridge. Footings and foundations. The part of the foundation of a structure which rests on earth. Foundation, substructure through which the loads are carried to the earth or rock. So this is your footing slash foundation. These two terms here, they're pretty interchanging. Footings usually don't have any type of material carrying a load down to the bedrock. Footings usually like a spread footing. It's just a concrete slab which distributes out the load according to that slab straight to the earth. Here in this case we have piles and a drill shaft which carries the load straight down to bedrock or to resistance per the design. This whole structure here is called the foundation. You got your piles, concrete, steel, or wood member driven into the ground to support a load. Here's your piles. In this example, this abutment here, it shows that you have two piles. One pile is driven straight, the back pile is driven straight down, and the front pile is driven at a slope of 1.5 inch per foot, 1.5 inch to foot slope. The pile cap is a structural member placed on top of the piles and used to distribute loads from the structure to the piles. And this is represented by this dotted rectangle here. And another thing, just to back up, if you notice how these lines are continuous, and then once you get to the concrete they're dotted, all this is showing that this section of the pile is actually up inside of the cap of the abutment. Columns, a vertical structural member supporting a floor beam, girder, or other members, and supporting primarily vertical. In this case, here's your column, your foundation, the drill shaft here. The column directly sits on top of that drill shaft and continues vertically. Your bent cap is a reinforced concrete beam or block extending across and encasing the head of columns, comprising the top of a bent for bridge span above. Here's your bent cap. It sits on top of your columns. And in every situation here, the reinforcement continues up. The only thing that continues up with this is the reinforcement. So when you pour your drill shaft, you'll have splice rebar penetrating through the top of your drill shaft. When you pour your column, you'll have hooks penetrating out of your column that will be poured to integrate the cap into it. So you'll see that once you get into the details of your bent. Last but not least, you have the wing wall. It's a retaining wall at the end of a bridge or culvert to retain the earth, and it's shown here. So you'll see these on your abutments. You have to, if you have any type of slopes or any type of buildup approaching to your bridge, you will have wing walls coming off the side. And as we discussed in our past videos here with the cross-sectional cuts, you got your cross-sectional cut A and B. This represents your abutment where your actual roadway is going to sit, and the B sectional cut represents your wing wall. And if you look up here at your plan view, you'll notice there's a big difference between how your wing wall is built and your abutment seat. Forms. Temporary structural molds usually made of wood, fiberglass, metal, or plastic for the support of concrete while it is setting and gaining sufficient strength to be self-supporting. And here's an example of forms. That's a pretty column. Superstructure. Superstructure, frame of the structure, usually above grade, portions of a bridge above piers and abutments. Here's a cross-sectional view of your bridge. Here's your superstructure, and just just keep in mind your superstructure is your bearing pads and up. It's what the traveling public drives on. Parts of the superstructure is your elastomeric bearing pad, steel beams or concrete girders, tops of joints, overhangs, and barrier rail. Your bearing pads. Now these bearing pads right here, when it comes to a bridge, they can range from a 750-pound monstrosity as you see here, that require a crane and whole crew to set, and they range from that to a 3/8, 3/4 inch, 1 inch thick piece of rubber, neoprene rubber. So looking on your plans, it will tell you what kind of bearing pad that you're going to be setting. Here in this case, it's a Type 4 Mark VB1 abutment 1 bearing pad. On abutment 2, you got a Type 2 Mark B1 bearing pad. Not much of a difference. Steel beams and concrete girders. They're not called beam girders. They're called girders and beams. Here's prime examples. Over here on the left, you got a box girder, concrete box girder, precast box girder. Yeah, this girder was 4 foot wide, 2 foot tall, 70 foot long. They also have bull T girders and ashtoe girders, Type 1s, 2s, and 3s. They're all typically used with DOTs on DOT bridges, and they're pretty. Each state may call them a different thing, but they're still the same thing. Over here on the right, you got a 84-inch steel beam on a continuous span. You got your splice here going across the river. Types of joints. You'll find your joints at your abutments where your roadway meets your bridge. You'll find an open joint. There's also closed joints, which is just a cut transverse with a bridge. So in this example, we have an 1.5 inch open joint at 70 degrees. Disregard that 70 degrees. In this case, it's a bridge joint armor. These are also called road irons. They're installed prior to pouring the deck. ALDOT requires armor joints, finger joints. People like GDOT, states like GDOT, they don't require armor joints, but they do require an open joint. So just it's plan specific. And this is typically how joints are sealed up, with a foam backer rod and the ALDOT or DOT approved sealant, whatever sealant is specified. Overhangs. This is how your overhangs of your bridge deck's poured. These things are designed to support the edges of the slab, and always the means of paving said road, whether it be a bidwell, razorback screed, Hugert screed, whatever. Here in this case, it's going to be a bidwell with your pipe rails, and these have to be engineered. And last but not least, your barrier rails is a typical through section. Design of the rail is going to differ state to state, but I would say 75% of the layout's the same when it comes to rebar. You just have to refer to your standard drawings and how it's per the plans. And last, this is an example of a barrier rail that was done in Alabama. This is pre-rubbing. Looks beautiful. Good job, Steve Turner, and he did 4 of those. So, okay, thanks for watching episode 5. Leave a comment, send me an email, or just kind of throw something at me if you need it. If you got a question. Okay, thanks.